Charged tapes. In this experiment, I observed the interactions between two charged pieces of tape with each other as well as the objects in the surroundings. Using this data, I determined the net charge on a single piece of tape and then created a computational model to display the interaction between two pieces of charged tape in a controlled environment. To create charged tape, a piece of base tape was smoothed onto a desk, and two pieces of tape, each measuring 20 centimeters with a mass of 0.2 grams, were stuck onto the base tape, then removed, resulting in a transfer of electrons to the base tape, creating a charge. These tapes were then tested against a negatively charged plastic pen, where they experienced attraction to the pen and were therefore determined to have a net positive charge. Once the two charged tapes were created, one tape was attached between two books and the other was held underneath it, gradually moving closer until an interaction occurred. When the two tapes were roughly 4 centimeters apart, the upper tape began to repel from the lower tape and rise upward. Using the mass of the upper tape, the gravitational force on the tape can be calculated. Gravitational force is equal to mass times gravity, where m is the mass of the tape and g is the gravitational constant. Using these values, we got a value of 0.002 newtons for the gravitational force. Using fundamental physics principles, since the floating tape was motionless and the two forces acting on the tape were gravity and the electric force from the lower tape, the electric force can be quantified as equal to the gravitational force moving in the opposite direction. Therefore, the electric force is also 0.002 newtons. With the quantities of gravitational and electric force known, and under the assumption that the two tapes are identically charged, the net charge on the tape can be calculated. First, the electric field at the location of the upper tape can be calculated using the equation the field is equal to kq over the magnitude of r squared times r hat, where k is Coulomb's constant, q is the charge of the tape, r is the distance from the lower tape to the upper tape, and r hat is the unit vector in the direction of r. With the calculation of the electric field, the electric force can be calculated using the equation electric force is equal to Q times E, where Q is the charge of the tape and E is the electric field. The equations for electric field and force can then be combined into electric force is equal to KQ squared over R squared times R hat. Since the electric force value is known, the equation can then be rearranged into Q equals the square root of the electric force times the distance squared over K. With this equation, we calculated the value to be 1.18 times 10 to the 11th elementary units, or 1.9 times 10 to the negative 8 coulombs for the charge. Once the net charge of the tape had been quantified, a computational model was created to observe the behavior of the two tapes in a virtual space. By plugging in the net charge calculated in the experiment, along with the measured mass of the tape, the model was created to represent the tapes as a line of point charges and display their interaction at a distance of 4 centimeters. When the model was run, the gravitational and electric force were measured as follows. Gravitational force was measured to be 1.962 times 10 to the negative 3 newtons downward. The electric force was measured to be 0.0470078 newtons upward. Question: what would change if electrons and protons had opposite charges? If the charges of electrons and protons were to switch, I believe that the interactions between the charge tape and external objects would reverse, but interactions between the two tapes would remain the same. When the tape moved towards my hand during the charge test, if the tape were to have an opposite charge, it would have repelled instead of attracted. However, since the two tapes were charged in the same way, they will always have identical charges, so the repulsion which causes the top tape to hover in the experiment would still take place.